Today we're going to explore the Model Context Protocol, or MCP, a revolutionary approach to how humans and AI communicate. Whether you're a developer or just curious about AI, this guide will help you understand one of the most important innovations in AI communication. Let's begin our journey into making AI more useful and understandable for everyone. Here's our roadmap. We'll start with an introduction to what MCP is, explore its core components, examine the technical architecture, see real-world applications, discuss the benefits, and look at the future of MCP. By the end, you'll have a clear understanding of how MCP is transforming AI interactions. Let's start with something familiar: visiting a restaurant. When you dine out, there's a complex communication system at work. You need to communicate what you want to eat. The waiter needs to understand your order correctly. The chef needs to know exactly how to prepare your meal. And everyone in this chain needs to speak the same language to avoid confusion. This communication challenge is exactly what MCP solves in the AI world. It creates a universal language that helps humans, applications, and AI models understand each other perfectly. Before MCP, the AI landscape was fragmented and complicated. Users don't naturally speak AI language. Applications needed complex custom code to translate user requests. AI models required highly structured instructions in specific formats. Without a standard approach, every company and developer had to create their own solution. This fragmentation led to inconsistent user experiences and made developing AI applications much more difficult than it needed to be. It was like having a different communication system for every restaurant you visited. In simple terms, MCP functions as a universal translator in the AI ecosystem. It helps people express their needs to AI in natural ways. It helps applications give clear, structured instructions to AI models. It helps AI understand exactly what's expected and how to respond appropriately. And it ensures everyone in this chain is speaking the same language. MCP bridges the gap between what humans want to accomplish and what machines need to execute those tasks. It's like having a skilled interpreter who perfectly understands both you and the AI. From a technical perspective, MCP is a standardized protocol that does 4 critical things. First, it structures AI system prompts in a consistent way. Second, it defines tool APIs and capabilities that extend what AI can do. Third, it specifies expected output formats so responses are consistent. And fourth, it maintains conversation state so interactions feel natural and coherent. This creates a common framework that works across different AI models, different companies, and different applications, truly a universal standard for human-AI communication. To understand the value of MCP, imagine visiting a foreign country without a travel guide. You don't know the local customs or language, you can't find important locations, you misunderstand cultural context, and each interaction becomes difficult and frustrating. This is what it's like using AI without MCP. The AI might understand parts of what you want, but there's no framework to guide the interaction, leading to confusion and inconsistent results. It's like being lost in a foreign land without a map or translator. Now imagine that same foreign trip, but with an expert local guide. You get clear explanations of customs and language. You have direct routes to important destinations. You understand cultural context for meaningful experiences, and every interaction becomes smooth and enjoyable. This is what MCP does for AI. It gives AI the guidance it needs to understand you better, access the right tools, format responses correctly, and remember previous interactions. The result is AI that feels much more helpful and intuitive. Looking at the technical landscape before MCP, we faced several significant challenges. Prompt engineering techniques were fragmented and inconsistent across different AI models. Tool integration methods varied widely between platforms. Every AI system had its own formatting requirements and expectations, and conversation handling was proprietary and siloed. The most frustrating part? Developers had to rebuild everything from scratch for each AI model they wanted to work with. It was inefficient, expensive, and slowed innovation significantly. MCP addresses these challenges through 4 essential pillars that work together seamlessly. First, context definition establishes the AI's identity and knowledge boundaries. Second, capability infrastructure defines the tools and actions available to the AI. Third, response specification sets clear expectations for output format and style. And fourth, state management handles conversation history and memory. Together, these components create a comprehensive framework for AI interactions that's both powerful and flexible. Before we dive into the components, it's important to understand the theoretical foundation of MCP. It's built on 4 key principles. Composability allows components to be mixed and matched, like building blocks. Extensibility means new capabilities can be added without breaking existing ones. Abstraction hides complex implementation details from users. And standardization creates common interfaces across different systems. These principles ensure MCP can evolve with technology while maintaining backward compatibility, a crucial feature for any lasting protocol. The first component, context definition, is like giving an actor their character background and script before a performance. It defines who they're playing, their identity, what knowledge they have access to, how they should behave, their personality, and what situations they'll appear in, their scope. Context shapes how the AI understands its role and responsibilities in every interaction. It's the foundation that determines how the AI will approach conversations with users. From a technical perspective, context definition includes several important elements. System role specification defines whether the AI is acting as an assistant, tutor, analyst, or another role. Knowledge cutoff dates and domain restrictions set boundaries on what information the AI can access. Behavioral parameters specify formality level, creativity, and detail expectations. And ethical guardrails establish clear limitations on responses. Here's a simple example. You are an AI medical assistant. Provide general health information, but always clarify you're not a doctor. Knowledge cutoff, 2023. Maintain a professional, empathetic tone. This brief context immediately shapes how the AI approaches health-related questions. The second component, capability infrastructure, or simply tools, is like defining a superhero's special abilities. It specifies what powers they possess, when they can use them, how the powers work, and any limitations that apply. Tools extend AI beyond simple conversation into meaningful action. Without tools, an AI can only discuss the weather. With the right tools, it can check tomorrow's actual forecast for your location and suggest whether you'll need an umbrella. Technically, tool definitions include function signatures with parameter types and constraints, API endpoints for external service integration, authentication methods for secure access, and error handling procedures for when things go wrong. Here's a simple example of a weather tool definition. It has a name, weather forecast, a description of what it does, and parameters including location, required, and number of forecast days, with a default value of 1. This structured definition allows the AI to know exactly how to use this capability when appropriate. The third component, response specification, is like providing a pre-designed form for the AI to fill out. It indicates which sections to include, how to format each section, which elements are required versus optional, and the overall structure and appearance of responses. Format ensures consistency and clarity in AI responses. Without it, the AI might provide information in different ways each time. With proper formatting, users always know what to expect and where to find the information they need. In technical terms, format specifications include output schemas defining required fields, markup requirements, like JSON, XML, or Markdown, internationalization parameters for different languages, and length constraints to control verbosity. A format directive might look like this. Provide answers in the following structure. 1. Brief summary. 2. Detailed explanation with code tags for code. 3. Real-world example. 4. Common mistakes to avoid. This structure helps users quickly find the information most relevant to their needs. The fourth component, state management, is like keeping detailed notes during an ongoing conversation. It tracks what was previously discussed, important facts that were established, decisions already made, and questions that still need addressing. Memory makes conversations with AI feel natural and coherent, rather than disjointed and repetitive. It's the difference between talking to someone who remembers your preferences and history versus explaining everything from scratch each time. From an implementation standpoint, state management includes message history storage and retrieval, user preference tracking across sessions, context window management for long conversations, and attention mechanisms that highlight particularly important information. Here's what this might look like in practice. The system remembers user Lee is planning a trip to Japan during cherry blossom season, has already booked flights, and is now looking for accommodation recommendations in Kyoto. This context makes the entire interaction more natural and efficient. MCP implements a sophisticated multi-layered architecture. The transport layer determines how MCP data is transmitted between systems. The structure layer organizes the 4 core components we've discussed. The semantic layer handles meaning and interpretation of the content. And the application layer manages domain-specific implementations. Each layer handles a specific aspect of communication, creating a robust and flexible system that can adapt to different needs while maintaining consistency. When implementing MCP, there are several crucial technical aspects to consider. Versioning ensures backward compatibility as the protocol evolves. Extension mechanisms allow for custom capabilities beyond the standard features. Validation schemas provide error checking to maintain data integrity. And security considerations protect sensitive operations and user data. These implementation details might seem technical, but they're essential for ensuring MCP works reliably in real-world applications, where stability and security are paramount. Let's see how MCP transforms real-world applications, starting with customer service. Imagine a company implementing an AI customer service assistant using MCP. The context defines it as a professional support agent for an electronics retailer with specific product knowledge. The tools include order lookup capabilities, return processing systems, and access to a knowledge base of common issues. The format specifies clear step-by-step instructions with an empathetic tone focused on solutions, and the memory recalls each customer's history and any previous issues they've reported. This MCP configuration creates significant benefits. Customers experience consistent support across all channels, web, app, or phone. There are seamless handoffs between AI and human agents when escalation is needed. Integration with CRM systems becomes much simpler, and policy updates can be made centrally and immediately reflected across all touchpoints. Here's what this looks like in practice. When a customer says, "My order hasn't arrived yet," the AI responds, "I'm sorry about the delay with order number 12345. I've checked our shipping system and see your package is at the local distribution center, scheduled for delivery today before 5 p.m. Would you like me to send you a tracking link?" A response that's helpful, accurate, and empathetic. In healthcare, MCP enables sophisticated patient support systems. The context establishes a health information assistant with medical knowledge and appropriate disclaimers. The tools include appointment scheduling, medication reminders, and symptom analysis capabilities. The format ensures clear explanations with medical term definitions and verification prompts, and the memory maintains patient history, preferences, and records of previous consultations. This configuration creates a healthcare assistant that's both helpful and responsible, with appropriate guardrails for this sensitive domain. The technical implementation for healthcare applications includes several specialized features. HIPAA-compliant data handling protects patient privacy. Integration with electronic health records provides accurate medical context. Clinician review workflows ensure sensitive recommendations are verified, and multi-language support serves diverse patient populations. When a patient asks about a medication like metformin, the AI provides comprehensive information about dosage, side effects, and important monitoring requirements, while still maintaining appropriate medical disclaimers and encouraging proper medical supervision. In education, MCP creates personalized tutoring experiences that adapt to individual students. The context establishes a patient, encouraging tutor with subject expertise. The tools enable interactive problem-solving, visualization of complex concepts, and tracking of student progress. The format implements Socratic questioning techniques, gradually revealing hints, and celebratory feedback for successes. And the memory tracks each student's learning style, previous misconceptions, and concepts they've already mastered. This creates a tutor that adapts to each student's unique needs and learning journey. Educational applications showcase some of MCP's most advanced capabilities. Adaptive difficulty adjusts based on student responses, becoming easier or more challenging as needed. Personalized learning paths are crafted for different student profiles and goals. Multiple explanation strategies are available for difficult concepts, shifting approaches if the student doesn't understand. And recognition of common misconceptions helps identify and correct fundamental misunderstandings. When a student says they don't understand quadratic equations, the AI responds with step-by-step guidance tailored to their previous knowledge, learning style, and pace, creating a truly personalized educational experience. Now let's explore why developers are enthusiastic about MCP. It's like having a universal power adapter when traveling internationally. It works in any country, with any AI model, adapts to different outlets, platforms, converts current safely, standardizes communication, and is a single device for all your needs, one implementation. The result? Developers can write code once and deploy it everywhere, dramatically reducing development time and maintenance complexity. The technical advantages for developers are substantial. Model portability means the same code works across different AI providers, allowing easy switching between models. Reduced boilerplate eliminates repetitive code for common tasks. Faster prototyping enables rapid experimentation with different configurations. And simplified maintenance means central updates propagate everywhere automatically. Users may not know about MCP directly, but they certainly experience its benefits. Consistency across different applications means learning one system translates to others. Personalization follows users everywhere instead of being siloed in individual apps. Reliability in how AI responds creates user confidence, and expanded capabilities allow AI to solve more complex problems than ever before. The result is AI interactions that feel more human-centered, intuitive, and genuinely helpful. These benefits translate to practical improvements in everyday experiences. Your shopping assistant remembers your preferences for size, style, and budget across all stores. Your health app gives advice that builds on previous conversations rather than starting from scratch. Your smart home controls understand precisely what movie night mode means in your household. And your travel planner recalls your preferences for hotels, flights, and activities when making recommendations. The common thread? AI that truly understands your preferences and needs, not just responding to isolated commands. Beyond practical applications, MCP has profound implications for AI development. It creates separation of concerns between model capabilities and application logic, simplifying system design. It enables composable AI systems where components can be mixed and matched like building blocks. It establishes interoperability standards across the AI ecosystem. And perhaps most importantly, it democratizes AI by making powerful capabilities accessible to smaller developers and organizations. MCP isn't just a technical standard, it's reshaping how we conceptualize and implement human-AI interaction at a fundamental level. Looking to the future, several exciting research directions are emerging. Multi-agent systems are using MCP for coordination between different specialized AI agents. Self-modifying protocols are being developed that adapt to user patterns automatically. Context optimization techniques are addressing challenges in large-scale applications. And cross-modal extensions are expanding MCP's capabilities to voice, vision, and multimodal systems. As AI capabilities continue to evolve, MCP will evolve alongside them, maintaining its role as the bridge between human needs and AI capabilities. Of course, challenges remain to be addressed. Privacy considerations in state management must balance personalization with data protection. Standardization across competing providers requires industry cooperation despite competitive pressures. Governance models for protocol evolution need to balance innovation with stability. Performance optimization for complex contexts must address computational efficiency, and accessibility requirements must ensure these systems work for diverse user populations. How we address these challenges will significantly influence MCP's long-term impact and success. As we wrap up, let's review what we've learned. MCP establishes a common language between humans, applications, and AI models. Its four core components, context, tools, format, and state, work together to create consistent, powerful AI experiences. Context defines who the AI is and what it knows. Tools determine what the AI can do beyond conversation. Format specifies how responses should be structured, and state maintains memory of previous interactions. Together, these components create AI experiences that are more intuitive, more capable, and more helpful than ever before. MCP matters because it brings significant benefits to everyone in the AI ecosystem. Users enjoy more consistent, helpful AI interactions across different applications. Developers benefit from simplified implementation and reduced duplication of effort. Businesses achieve faster deployment, better integration, and future-proofing of their AI investments. And the entire AI ecosystem gains interoperability, innovation capacity, and accessibility. In short, MCP bridges the critical gap between human needs and AI capabilities, making artificial intelligence more accessible and useful for everyone. In the big picture, MCP represents a transformation of the AI landscape. Fragmented systems become a unified ecosystem. Inconsistent experiences transform into reliable interactions. Limited capabilities expand through extensible tooling. Complex integration simplifies with standardized implementation, and isolated applications connect through interoperable services. MCP is the universal language making AI more accessible, powerful, and human-centered. It's not just improving today's AI interactions, it's laying the foundation for a future where AI truly understands and serves human needs effectively. Thank you for joining me on this exploration of the Model Context Protocol.